and some device physics, and then in the second part I will probably race you through some of the prototypes that we've made using solution processed organic photodetectors. So we're interested in the topic because essentially there are a number of applications where CMOS does not quite do the job, because what you would like to have is a large area and in some cases even a flexible image sensor. And silicon is good if you want high performance on small area, then I think nothing beats silicon. But if you talk about large area, it becomes very expensive. And one of the best examples for organic photodetectors actually are flat panel X-ray detectors, because it's very difficult to collimate X-rays. So essentially you will have a flat plate detector that detects the X-rays, and typically these plates are 30 by 40 centimeters. Another application that we will be talking about is for biometric and for biomedical applications. But I will get there at the end of the presentation. So the type of photodiodes I don't need to introduce, has already been introduced very well by Koen. We use a bulk heterojunction device which we sandwich between top and bottom electrode. And then this was already also introduced by Koen. We want to make a sensor, which means that we are very much interested by the minimum amount of light that we can detect, which means that we want to have a low dark current, and actually it's the noise of the dark current, and we want to have a high photo response, especially at very low light intensities. Now, it was already mentioned that typically in most of the photodetectors, the way you read it out is in capacitive mode. So that means that you apply a reverse bias, and typically what you will see at these higher reverse bias, that the dark current will be higher than the intrinsic limits that Koen was talking about. And I also would like to come back to that point a little bit, because what Koen was talking about was essentially this J0 of the Schottky diode, which essentially is the thermal noise due to thermal charges being generated and recombining. We will show that when you apply a large bias or a relatively large reverse bias, that we also suffer from other issues in these kind of devices. So let me show you a few polymers that we actually studied. Here you see they're well studied. So they're DPP polymers. There's very old PPV polymers. There is a DPP polymer which has the lowest band gap and still is able to give a good bulk heterojunction in combination in all cases with this very well-known PCBM. So essentially by combining 5 polymers with this one acceptor, we can look at the different energy levels, the different band gaps, and see actually what happens if we blend these different materials and compare the dark current. And then after the talk of Koen, it's not a surprise that the dark current in fact scales exponentially with the open circuit voltage of these devices. And what you also see is that this dark current then changes by going from a high bandgap material to a low bandgap material. It changes 5 orders of magnitude, which is an awful lot. And essentially what you still do not know is this is the sort of the experimental open circuit voltage. So you don't know whether this is due to the intrinsic limits that Koen was talking about, so assuming thermal charge generation, or whether it's due to, for instance, charge injection from the contacts. So this has been reported also by others. We also looked at the temperature dependence, and that was initially quite surprising to see that despite the large variation in the absolute value of the dark current, the activation energies of the dark current in all these different devices was very similar. And was relatively low. So you see that it's not perfectly described by a single activation energy, but if you would do that over this range, then you would see that the activation energy is about 0.25 electron volts, which is remarkable if you think about these type of materials and the energies. It doesn't really make sense, this 0.25 electron volt. So we looked a little bit more on how we could essentially explain that. And for reasons that I will not go into today, we discarded that in our devices, these dark currents were due to the bulk thermal generation. And in fact, we started to look if we can model both the temperature dependence as well as the absolute dark currents using charge injection as the main mechanism. Now, if you want to inject charges from a non-ohmic contact in these organic materials, then the injection current is essentially proportional to the amount of charge carriers that you can inject times their mobility. And if you then look at this N0, which is given by this uphill process energetically, you can at least modify the injection barrier, taking into account that these materials are disordered. So you don't need to inject in the top of the gauge, but essentially you can inject in the tail of this Gaussian disorder in the states here. Plus you can also take into account the barrier lowering due to the image potential. So that's what we actually take into account in our model when looking at the effective injection barrier at which you want to inject. The second thing is the mobility, which we all know is in these organic materials is density and field dependent. And what we actually set out to do is to actually calculate or fit this mu0 using space charge limited measurements on unipolar devices of the different blends. And then we can fit that with a certain model. I'm not going to go into the details, but it's the what's called the extended Gaussian disorder model. So then we have an expression of the mobility here and a approximation of the amount of charges that are actually injected. So if you look then at the product of both, then you get this equation. You actually see that there's quite some terms in there, but most of them actually we can experimentally determine. I should point out that there's always ambiguity about what is the exact HOMO and the LUMO level, but this sigma essentially is coming from the charge transport measurements on the devices. And if we then start to use this equation to model the temperature activation, you see that we can do that quite accurately. So that makes us very happy. However, if you look more carefully, then we needed somehow to work with a Gaussian disorder term, which is 40% larger than the actual disorder term as derived from the bulk charge transport measurements. There are possible reasons for that. You could assume that the disorder at the interface where the injection takes place is larger than in the bulk, but the truth is it's an assumption. We don't have experimental proof for that. The second is perhaps even a little bit more problematic because this proportionality factor A should be close to 1, but essentially it's much smaller than unity. So yes, we can describe the temperature activation using this model and then assuming that in our case the dark current is determined by charge injection, but you see that in the details there's still improvement possible. I want to show this because especially in our devices, when we start to characterize the dark current at much lower voltages, then we see trends which are much closer to actually Koen has been presenting before. So at low voltages, it seems that charge injection is not as dominant, but at these high voltages it is. So let's move over to actually doing stuff with these organic photodetectors, talking about 2D arrays of the organic photodetectors. Then you also understand why I sort of focus on this aspect of high reverse bias. So before actually going into the schematics of how we read out these diodes, this is a cross-section of the type of detectors that I will be talking about. So on top you have your organic photodetector, and underneath that we have a backplane of, in this case, amorphous oxide thin film transistors. We also have the possibility to encapsulate the bulk heterojunction devices on top and below, using, in this case, the top barrier should of course be transparent, but also in some cases it should be very thin. So these three components make up the detectors that I will be talking about in the rest of the presentation. So a few words actually on how the standard readout of such a device is. And so essentially you have a thin film transistor that switches, I should say that essentially puts a voltage, a reverse voltage on this node. And by doing that, you actually store charge on this diode. Remember, it's in the reverse, so it acts basically as a capacitor. Now, if you don't shine any light on that, then that charge should be on there forever. However, if there is some light, then you slowly get a change in the voltage at this node. If you operate such an array at not sufficiently high bias, then at one point in time you will see that you are no longer in the capacitive mode. And that's the reason why you need quite a high reverse bias. -2 volt is sort of the minimum. Ideally, you would like to go to -5 volts. Then after a while, you open this transistor and then you restore this potential node to the value that you want, and you can detect the amount of charge that is needed for that using external charge sense amplifiers. So here in Eindhoeven, we're pretty well equipped when it comes to making devices on large areas. So both the organic photodiode technology as well as the backplane technology we can do on plastic substrates as large as 30 by 35 centimeter. And we can stack them on top of each other, and then we can actually characterize full prototypes. And this is a prototype where we actually have an area of 6 by 8 square centimeter. It's in this case on a polyimide plastic film, which is about 15 microns thick. We have a VGA format. It's about 200 ppi. These are just some numbers. This makes it very interesting because the sensitivity of this detector, so within the array, we have a dark current density which is less than 3 × 10⁻⁸ milliamps per square centimeter. And an EQE in the best case is about 60%. These are very good numbers. There was in the previous session a question about, does this outperform silicon? No, it does not outperform silicon simply because of noise, but it is really on par with amorphous silicon. And amorphous silicon is currently the choice for making these large flat panel detectors. If you would calculate the specific detectivity from these numbers, then you will get a specific detectivity which is about 10 to the 14th joules, which is even a little bit higher than silicon, which should make you wonder, because indeed you can't use this formula to calculate the specific detectivity. If you do it the right way, by actually looking at the noise current at relatively low frequencies, then we get a factor of 30 lower specific detectivity, which is a decent value, but you see it falls short on the 10 to the power 14 that you get for silicon. Nevertheless, we're not trying to compete with silicon here. We're trying to establish a new technology for large area detectors. The final thing which I would like to mention here is the linearity. So typically, when you look at these kind of characteristics at relatively high intensities, most of these devices are pretty linear. But the question is, how far does this extend when you want to go down in light intensities? Remember, one of the applications is X-ray detectors. You want to limit the dose that you need for every patient. So you really want to operate your image plate in this regime. And here you see that actually we can see a quite good linear response down to, in this case, values of 3.5 nanowatts per square centimeter. Showing some actual images that we captured with these detectors. If we put a semi-transparent slide on top of the detector and shine light from above, then we can capture a photograph. But we can also shine light from the bottom. And then part of that light is reflected, but part of that light is going through actually the detector and then can bounce backwards if an object is in direct contact with the detector. So in the next movie, what we actually do is we throw a dice on the detector. There is light coming from below, and you'll see that as soon as the dice is getting in contact with your detector, you get a sharp image. Actually, this is a prototype that we built for a company, and we presented it at the CES in Las Vegas. That's why they were so interested in dice. We're interested in more other type of applications, one of them being biometric imaging. So the scheme is exactly again shown here. So there's light going through all the different layers, and then when you put your finger on top, essentially part of that light is reflected back, and that light is then detected by a photodetector, and essentially you can see an image. And here you see the hand being placed on the detector, and you see that in this case, and that's nice, you can capture the fingerprints of 4 fingers at the same time. If you want to go to really secure biometric applications, then your photo imager needs to have a minimum resolution of 508 ppi. That's the one of the FBI standards. So we made a detector which has this higher resolution, and that's simply done by patterning the bottom electrode to smaller islands. And the good news is we can do that by just patterning this metal layer, because we do not need to pattern the organic photodiode per pixel. That is something that you need to do in case of amorphous silicon. So that is another advantage of using these organic photodetectors, and you can basically intuitively understand why it's not so important to pattern them per pixel, because mobilities are low in these devices and these layers are very thin. Typically in our photodetectors we use a layer thickness of about 300 nanometers, which means that there is very little spillover from the charges which are generated in one pixel to the next pixel. And then you have a blanket layer of photodetectors, of photoactive layer, and you can detect high quality fingerprint scanners. And if you're an expert in the field, then you're not so much impressed by the contrast of these valleys and the ridges, but you actually want to look at the sweat pores and the minutiae. And you can see them very clearly in this image here. So that's nice. And one of the applications which we are working on is trying to integrate such a large area detector into a mobile phone display. We all see that the power button, which used to contain the fingerprint scanner, has disappeared because we want more display. Well, basically we want the display to cover the full mobile phone. And then the question is, where do you put the fingerprint scanner? You can put it at the back, some companies do that, but ideally you would like to integrate a photodetector inside the mobile phone display. That's very difficult. The other thing that you could potentially do is make the photodetector semi-transparent, which sounds contradictory in the first time. So you want to make a light sensor, so how can it be transparent? Well, actually, it's not really transparent, but instead of using the full area for your organic photodiode, we only per pixel have a active area of 5 by 5 micron where we detect the light. So then from a certain distance, your eye can't see these patterns anymore and it looks like transparent. So here we have this semi-transparent photodetector and a mobile phone which is behind that transparent photodetector. If you would move in, you would see small patterns, and typically these patterns are the organic photodiode. Here we actually remove most of the photodetector, most of the photoactive layer that is coated on there for the first time. So in order to make that transparent, you use another photolithography step. Just to show you that we can also, for the semi-transparent detector, we can detect fingerprint scanners. So this is your mobile phone, it's behind the transparent photodetector. You'll see in a moment somebody pushing the finger here, and you'll see the image being recorded. And this is just one way of how you could integrate the photodetector with a mobile phone display. If you choose the right wavelength, you're also not just reflecting at the surface of your skin, but part of the light is actually moving into your fingers and is then reflected back onto the photodetector. And because your heartbeat, you actually have a pulsation in the arteries. And it's a very small signal, but if you have accurate readout, you actually can, just by placing your finger on there, record your heartbeat. Which is nice, which is I would say, an additional feature to make such an imager work as a very good biometric imager. This is some sort of liveness detector. You can also do that with 2 wavelengths, and then by looking at the ratio of the response of, in this case, a near-infrared wavelength with a red wavelength, you can calculate the oxygen saturation. The problem with just doing that with 2 photodiodes is that you always need some calibration. But if you use an array of photodiodes, you actually get information from the spatial distribution. If you do not illuminate your detector full plate, but actually just with a local spot. So that's a way to actually calculate these oxygen saturations without an external calibration. And here I'm talking about SpO2, oxygen saturation, but it's the full waveform of your heartbeat contains a lot of information on your physical fitness. If you extend the wavelength even more into the near infrared, and I think this is one where we extended up to 1050 nanometers, you clearly start to also see the vein patterns. And like your fingerprint pattern, the vein patterns in your hand are unique for every individual. So this is yet another way of making a biometric imager. In times of COVID, people don't like to actually touch these kind of images. So here we actually did remote monitoring of this vein detection by including a lens. Finally, my title, I also promised you flexible imagers. And here you see an example of where flexibility actually makes sense. So we have a flexible image sensor. I didn't mention it, but the total thickness of that flexible image sensor is about 100 micron. So it's really thin. If you combine that with a standard scintillator, which is used in indirect X-ray detectors, we can make a curved detector. So this scintillator actually can absorb X-ray photons. That's why it needs to be quite thick. And upon absorption of the X-ray photon, it emits green light. And this green light is then detected by our organic photodiode. And if you then look at some X-ray applications, you have an application where there is a flat plate detector combined with an X-ray source which is moving around the patient. And if you can replace that flat detector with a curved detector, essentially your whole system can become more compact. And initially we also were hoping to see that we would get better image quality in the corners of these flat plate detectors, or sorry, in the corners of this curved detector compared to the corners of the flat panel detector. So actually what we did, we made a system where this curved detector was actually rotating, and the X-ray source and the curved detector were fixed. And then every 2-degree turn of the object, we take an X-ray image. So essentially we have 180 X-ray images, and from that you can construct a very nice 3D reconstruction. You can do 3D image reconstruction and you get these very nice 3D images. The advantage of using a curved detector in that sense comes mostly from the fact that the system can be more compact. It is true, we also see less issues in the corners of this curved detector, but I also have to be honest that these kind of artifacts can be easily, well, not easily, but they are typically corrected with software. So that's not the main driver anymore. So that's summarizing my talk. We're not trying to compete with silicon. Well, we are, because we're interested in near-infrared detectors beyond 1100 nanometers. But I think the first thing which is already very encouraging is that we see that these organic photodetectors have a performance which is on par with amorphous silicon thin film diodes, where it has some clear processing advantages. And because of that, we believe there is a good future ahead for these materials in biometric and biomedical imagers. And then let me leave you with putting up the slides on the acknowledgements, and then thank you for your attention.
Thank you very much, Gerwin. Really, really fantastic talk. Okay, yeah.